Welcome back to another Sleepy Steve story. Before we drift off tonight, remember to subscribe to help Steve-O out, and I will keep making more sleepy stories to help you study gently, revise quietly, and settle your mind at the end of the day. Tonight, we are staying in Unit 3 Chemistry, Area of Study 1, and we are continuing to think about energy, fuels, and electrochemical ideas. In the last few episodes, we looked at fuels, combustion, thermochemistry, calorimetry, and galvanic cells. We thought about the way chemical reactions can release energy, the way that energy can be measured, and the way redox reactions can be arranged so that electrons move through an external circuit. Now, we are going to take those ideas one quiet step further. Tonight's episode is about fuel cells and sustainable energy. You might picture a calm science laboratory in the evening. The benches are clean, the lights are low, a diagram of a hydrogen fuel cell rests on the board. A small model car sits on the front bench, silent and still, waiting for chemical energy to become electrical energy and then movement. There is no flame in this room, no roaring engine, no smoke curling upward. Just the quiet idea that chemical energy can be transformed in different ways. Combustion releases energy quickly, often as heat and light. A galvanic cell releases energy by separating oxidation and reduction into two half cells, forcing electrons to travel through a wire. A fuel cell also uses redox chemistry, but it is designed so that reactants are supplied continuously and electrical energy can be produced as long as fuel and oxidant keep entering the cell. That is the heart of this episode. A fuel cell is an electrochemical cell that converts the chemical energy of a fuel directly into electrical energy through redox reactions. The word directly matters. In many energy systems, fuel is burned first, heat is produced, steam may be generated, turbines may turn, and then electricity is produced. There are several energy conversions along the way, and each conversion can involve energy loss. A fuel cell does not need to burn the fuel in the same way. Instead, it uses the movement of electrons from a redox reaction to provide electrical energy. So, as you settle into the story tonight, imagine the fuel cell as a quiet bridge between chemistry and electricity. On one side there is a fuel, often hydrogen. On the other side there is oxygen, often from the air. Between them is a membrane or electrolyte, carefully allowing some particles to move while keeping the process organized. And through the external circuit, electrons move. Slowly, calmly, usefully. Let's begin with the most common example used in VCE chemistry, the hydrogen fuel cell. A hydrogen fuel cell uses hydrogen gas as the fuel and oxygen gas as the oxidant. The overall reaction is simple to remember. Hydrogen reacts with oxygen to produce water. In words, hydrogen plus oxygen forms water. This is the same overall chemical change that can happen in combustion, but the energy is released in a different way. Instead of burning hydrogen in oxygen and producing heat, the fuel cell separates the oxidation and reduction processes so that electrons can flow through an external circuit. At the anode, oxidation occurs. Hydrogen loses electrons. A useful memory line is that oxidation is loss of electrons. In an acidic hydrogen fuel cell, hydrogen molecules are split into hydrogen ions and electrons. The electrons cannot pass directly through the electrolyte or membrane, so they move through the external circuit. That movement of electrons is the electrical current that can do useful work. At the cathode, reduction occurs. Oxygen gains electrons and combines with hydrogen ions to form water. A useful memory line is that reduction is gain of electrons. The cell keeps working because hydrogen continues to enter at the anode, oxygen continues to enter at the cathode, and water is removed as a product. A galvanic cell, such as a zinc and copper cell, has a limited amount of reactant inside it. When the reactants are used up, the cell stops producing electrical energy. A fuel cell can continue operating for much longer, provided the fuel and oxidant keep being supplied. This is one of the key differences students should remember. Fuel cells are not magical batteries that never run out. They still need a fuel. They still rely on chemical reactions. But unlike many simple galvanic cells, the reactants are fed in continuously so the device can keep producing electricity while the supply continues. Now let's slow down and compare fuel cells with combustion. Combustion of fuels is familiar. Petrol burns in a car engine. Natural gas burns in a heater or power station. Coal burns to heat water and produce steam. In combustion, chemical energy is usually transformed into thermal energy first. That thermal energy may then be transformed into mechanical energy and then electrical energy. Each transformation can reduce the overall efficiency because some energy is dispersed to the surroundings, often as heat and sound. Fuel cells can be more efficient because they convert chemical energy directly into electrical energy without using combustion as the main step. This does not mean all fuel cells are perfectly efficient. There are still energy losses. There may be heat produced. There may be losses in storing and transporting the fuel. There may be energy used to produce the hydrogen in the first place. But the direct electrochemical pathway gives fuel cells an important advantage when they are designed and used well. In VCE chemistry, an exam response should be careful here. It should not simply say that hydrogen fuel cells are clean. A stronger answer explains that when hydrogen is used in the fuel cell, the product is water, so there are no direct carbon dioxide emissions from the cell itself. But the environmental impact depends on how the hydrogen was produced. That final sentence matters. Hydrogen is often described as an energy carrier, not a primary energy source. An energy source is something from which useful energy can be obtained, such as sunlight, wind, coal, natural gas, or biomass. An energy carrier stores or transports energy that was produced from another source. Hydrogen does not usually exist on Earth as a large natural supply of hydrogen gas that can simply be pumped out and used. It must be produced from other substances, such as water or methane. So hydrogen can carry energy, but energy must be put in to produce it. This is a very important sustainability idea. If hydrogen is produced using renewable electricity to split water by electrolysis, then its overall environmental impact can be much lower. This is often called green hydrogen. If hydrogen is produced from fossil fuels, such as natural gas, then carbon dioxide may be produced during the production process. This means the hydrogen fuel cell may have no direct carbon dioxide emissions while operating, but the full life cycle may still involve greenhouse gas emissions. A strong chemistry answer looks at the whole system. It asks where the fuel came from. It asks how much energy was used to produce it. It asks how it was stored, transported, and used. It asks what products and wastes were formed. And it asks whether the process is sustainable over time. Now imagine the small model car on the science bench. Inside it, a fuel cell receives hydrogen and oxygen. The hydrogen is oxidized at the anode. The oxygen is reduced at the cathode. Electrons move through a circuit. The motor turns gently. The wheels begin to move. Water is formed as a product. It feels simple, but beneath the quiet movement is electrochemical design. For students, the key is to connect the visible outcome to the invisible chemistry. The car moves because electrical energy is supplied to the motor. The electrical energy is produced because electrons move through the external circuit. The electrons move because hydrogen is oxidized and oxygen is reduced. The fuel cell works because the oxidation and reduction reactions are separated, allowing electron flow to be directed through a useful pathway. That is the kind of explanation that turns a general answer into a chemistry answer. Now let's think about the parts of a fuel cell more carefully. There is an anode where oxidation occurs. There is a cathode where reduction occurs. There is an electrolyte or membrane that allows certain ions to move between regions of the cell. There is an external circuit where electrons move. There are reactant inputs such as hydrogen and oxygen, and there is a product output such as water. Different types of fuel cells may use different electrolytes, different temperatures, and different fuels, but the same broad electrochemical idea remains. Oxidation and reduction are separated. Electrons are directed through an external circuit. Chemical energy becomes electrical energy. For the hydrogen fuel cell, students should be comfortable explaining that hydrogen acts as the fuel because it is oxidized, while oxygen acts as the oxidant because it is reduced. Hydrogen loses electrons, so it is oxidized. Oxygen gains electrons, so it is reduced. The oxidizing agent is the species that causes oxidation by accepting electrons. The reducing agent is the species that causes reduction by donating electrons. In a hydrogen fuel cell, hydrogen is the reducing agent because it donates electrons, and oxygen is the oxidizing agent because it accepts electrons. This sounds technical, but it can be made calm and simple. Hydrogen gives electrons away. Oxygen receives them. The cell is designed so that the giving and receiving cannot happen all at once in the same place. So the electrons take the long way around, and that long way around is the useful current. Now we can link fuel cells to sustainability. Sustainability is not just about whether something sounds environmentally friendly. It is about whether the process can support current needs without compromising the ability of future generations to meet their needs. In chemistry, this usually means thinking about resources, emissions, efficiency, waste, safety, cost, reliability, and environmental impact. Hydrogen fuel cells have several possible advantages. When hydrogen is used, the main product is water. There are no direct carbon dioxide emissions during operation. Fuel cells can have high energy conversion efficiency compared with some combustion-based systems. They can be quiet because there are fewer moving parts than a combustion engine. They may be useful in transport, backup power, remote power systems, and situations where batteries alone may not be the best solution. But there are also challenges. Hydrogen has to be produced. If production relies on fossil fuels, greenhouse gas emissions may still occur. Hydrogen storage can be difficult because hydrogen gas has low density and may need to be compressed, liquefied, or stored in special materials. Transporting and storing hydrogen safely requires infrastructure. Fuel cells can be expensive, and some designs use rare or costly catalysts, such as platinum. There may also be questions about durability, availability, and large-scale implementation. A balanced answer includes both advantages and limitations. It does not pretend that fuel cells solve every energy problem by themselves. It recognizes that fuel cells are one possible technology within a broader energy system. Now, let's compare hydrogen fuel cells with rechargeable batteries, because this can help clarify the role of energy storage. A battery stores chemical reactants inside the cell. When the battery discharges, chemical energy is converted to electrical energy. A rechargeable battery can be recharged by using electrical energy to reverse the chemical process, at least to a useful extent. A fuel cell does not usually store all its fuel inside the cell in the same way. Instead, the fuel is supplied from outside. This means a fuel cell vehicle may be refueled with hydrogen, while a battery electric vehicle is recharged with electrical energy. Both technologies can be useful. Both depend on how the energy is produced. Both have strengths and limitations. For exam purposes, avoid simple claims like fuel cells are better than batteries, or batteries are better than fuel cells. Instead, explain the context. For example, batteries may be highly efficient for many everyday transport and storage uses, especially when charged from renewable electricity. Fuel cells may be useful where rapid refueling, longer range, heavy transport, or continuous operation is important, provided hydrogen can be produced and supplied sustainably. The best technology depends on the purpose, the source of energy, the infrastructure, and the environmental trade-offs. Now let's bring the chemistry back to the exam page. A question might ask why a hydrogen fuel cell can be considered more environmentally friendly than a petrol engine. A weak answer might say, because it is clean. A stronger answer would say, a hydrogen fuel cell converts chemical energy directly to electrical energy through redox reactions, and when hydrogen reacts with oxygen, water is produced rather than carbon dioxide during operation. An even stronger answer would add, however, the overall environmental impact depends on how the hydrogen is produced, because hydrogen made using fossil fuels may still be associated with greenhouse gas emissions. That final qualification shows a more complete understanding. Another question might ask students to explain the function of the membrane or electrolyte. A strong response would say that the membrane or electrolyte allows selected ions to move between the anode and cathode regions, helping complete the circuit and maintain charge balance while preventing the reactants from simply mixing and reacting directly. Another question might ask students to compare a galvanic cell and a fuel cell. A useful response would say that both are electrochemical cells that use spontaneous redox reactions to produce electrical energy, but a fuel cell requires a continuous supply of reactants, such as hydrogen and oxygen, while a simple galvanic cell has reactants contained within the cell and stops when they are depleted. Notice the pattern. Define the idea. Explain the chemistry. Link it to energy. Then evaluate the advantage or limitation. That is the calm exam rhythm for this topic. Now let's return to the quiet laboratory. The model car has stopped near the edge of the bench. The diagram of the fuel cell is still on the board. An arrow shows hydrogen entering one side. Another arrow shows oxygen entering the other side. A small line shows electrons traveling through the external circuit. And at the end, water forms quietly as the product. This simple diagram holds many Unit 3 ideas together: redox, oxidation and reduction, anode and cathode, electron flow, energy transformation, efficiency, sustainability, environmental impact. The important thing is not to memorize fuel cells as a disconnected example. The important thing is to see them as part of the bigger question of Unit 3 chemistry. How can design and innovation help optimize chemical processes? Fuel cells are a design response to an energy problem. They use chemical knowledge to produce electrical energy in a different way. They may reduce direct emissions when hydrogen is used. They may improve efficiency compared with some combustion systems, but they also raise questions about fuel production, storage, cost, materials, and infrastructure. That is why chemistry is not only about equations, it is also about choices. It is about evidence. It is about comparing options carefully. It is about understanding that a technology can be promising and still have limitations. So, as the episode begins to settle, let the key ideas become simple. A fuel cell converts chemical energy directly into electrical energy using redox reactions. In a hydrogen fuel cell, hydrogen is oxidized at the anode, oxygen is reduced at the cathode, and water is produced. Electrons move through the external circuit, providing useful electrical current. Fuel cells need a continuous supply of reactants. Hydrogen is an energy carrier, not usually a primary energy source. The sustainability of hydrogen depends strongly on how it is produced. Fuel cells can have advantages such as high efficiency and no direct carbon dioxide emissions during operation when hydrogen is used. But they also have limitations, including hydrogen production, storage, transport, cost, and infrastructure. A strong VCE chemistry answer explains both the chemistry and the context. And now, the laboratory is quiet again. The model car rests still on the bench. The fuel cell diagram waits on the board. The arrows are simple: fuel in, oxygen in, electrons around the circuit, water out, chemical energy becoming electrical energy, and a small reminder that the future of energy depends not only on what we use, but how we produce it, how efficiently we transform it, and how carefully we think about the world around us. This has been Sleepy Steve. Sleep well, and let the fuel cell settle quietly in your mind.